Okay, let's talk about diodes briefly. Let's review what we learned about diodes. So diodes are directional. They've got a positive side and a negative side, an anode and a cathode, and current flows from anode to cathode. And a diode is formed from a p-n junction. We talked about p-type material, p-type semiconducting material, and n-type material. And we put the p and the n together, and it creates this depletion region, which prevents charge from flowing, prevents electrons from flowing in the wrong direction. So it can only flow from P to N. This graph helps explain the behavior of a diode. We learned that for an ideal diode, which is the green line, we are going to assume that no current flows unless it is forward biased. And forward biased means that the anode is 0.7 volts higher than the cathode. Okay, and when that happens, we get current flow, and we say we get infinite current flow. But in reality, it will be limited by a current limiting resistor. If we reverse bias the diode, nothing happens, no current flows. Although in reality, diodes have a breakdown. And if we put too much voltage in the wrong direction, they will break and current will flow. Okay, we talked about LEDs, light emitting diodes, and how they have different voltage drops. So you want to look those up if you're going to be designing something with an LED, a circuit, especially if you're using a blue, it's 4.5 volts. So that's a lot different than a red, which is usually about 1.7 volts. Okay. All right, and just a final note, you have to current limit the LEDs, and we did this class exercise where we calculated the current, what size resistor we would need to limit the current for a blue LED. Okay, today we're going to talk about transistors, and you read about this in the reading. So a diode will prevent current from flowing, but what we would like to be able to control the amount of current. That would be even better. And so in the late 1940s, a magical device was invented that allows this. So imagine, if we're using our pipe flow analogy, imagine we've got this device where there's a ball blocking the flow of fluid, but if we put a little bit of fluid down this small pipe, it will push the ball out of the way, and a much bigger amount of fluid will be able to flow in the main pipe. And that's a good analogy for what we are able to do with a transistor. I'll show you some more, another fun animation. So here, we'll see what this chart means in a couple slides, but we control the transistor through the base. And if I turn up the base, I get this plunger moves out of the way, and I get more fluid flow through the pipe. Now, if you're looking at these numbers, this says 50 and this says 50, but look at the units. It's microamps versus milliamps. So this particular transistor would have a gain, what we call a gain of 1,000, which is pretty high. It's usually more like 100. So if we turn down the base, that plunger plugs the pipe and no current flows. Okay, we'll learn a little bit more about the physics now, how this actually works. Okay, so this is an actual, what a transistor looks like. I'm gonna get my notes going here. Let me see, so I think I'm gonna slide this over here. Can you guys see the slides okay?
So I think we're getting a little bit of lag from the. I think we're getting a little bit of lag from the animation.
Oh, on the animation. Okay, well, let's see if we get lag on the writing. There's nothing really I think I can do about it, but I hope we don't get that. So you could think of a transistor as a couple of diodes put together, and we're going to use that as an analogy. And there's three important parts of the diode: the collector, the base, and the emitter. And so this is the base, this is the collector, and the emitter will be down here. Whoops. And the reason we use this diode analogy is to show that current only flows in certain directions. So a bipolar junction transistor is physically created by sandwiching that N or P type material in this arrangement. This is what's known as an NPN transistor, but you can also have a PNP. And they're not exactly doped the same way, but for our purposes, we're just going to treat them all as the same. And with this arrangement, we're able to control a large current from the collector to the emitter by controlling the current at the base. So we call this a bipolar junction transistor, or a BJT for short. And we have the base, the collector, and the emitter. So these aren't physical diodes, but we're drawing them as diodes because I think it's an effective way of understanding how it works. The diagram on the lower left is indicating that we have a base current flowing through. We have we'll have a current flowing this way, and we'll have a current flowing this way. And these two currents, so this is the base current, and this is the collector current. And those two are gonna combine, base plus collector, to create an emitter current. The device turns on when the diode from B to E is forward biased. And what would that mean for a diode?
Greater than 0.6 volts for most of them.
Very good. So the voltage from B to E is greater than 0.6 volts. Okay, we consider that forward bias. So that means that the voltage at point B has to be higher than the voltage at E by 0.6 or more. Now, in order for this to work, the diode formed between C and B must also be forward biased. It's what we would call a necessary condition, but not a sufficient condition. Nothing will happen. And so what we mean by that is, so to summarize, we need to have the voltage at C has to be greater than the voltage at B, which has to be greater than the voltage at E. And there's actual quantities they need to be greater than, but we're not going to worry about that right now. And then we can also summarize Kirchhoff's current law plus equal IE. So in order to set this up to work, to have something happen, the voltage at C has to be higher than the voltage at the base, and the voltage at the base has to be higher than the voltage at the emitter. So a lot of what we're going to look at today is how do we design a circuit to make sure that happens. Okay, so we're going to learn about how you build a circuit. Okay. So how does this actually work? I think this is kind of interesting. The physics is really interesting. So this is diagram on the right is showing us our NPN material, and we see that there's an N++ and an N+, indicating that the emitter down here at the bottom is not exactly the same as the collector. That's not really important because we're not going to be building our own transistors, right? So let me pull up another animation that's kind of cool. I hope this one works. But the way this actually works physically is we have, so here, if you look at this this animation. This is the collector on the top, the emitter on the bottom, and the base, this small pipe on the left. Physically, what happens is when we get the transistor forward biased, meaning we built it into a circuit that is appropriate for that transistor, there will be an attraction for the electrons to be pulled from the emitter into the base. The base is so small that most of the electrons can't make it through the base. And in fact, but the attraction is so strong that it pulls those electrons towards the base with a lot of momentum, and the momentum actually pushes them across the depletion region into the collector. And so a current is drawn through the collector by what's going on at the base. So if we turn off the base, we don't get that draw pulling the electrons toward it, and no current will flow through the collector. As we turn on the base, we get that draw. So let's see how this works. So we make sure we have VCE on. That meets our first criteria. Remember that we said VC must be greater than VB. So we turn this on, so VC is greater than VB. Now we're going to turn up the base voltage. And this animation is kind of fun. We see the blue dots are the electrons. The electrons are down there in the N-type material in the emitter, and they're kind of hanging out. This depletion region is getting smaller as we turn up the voltage. When we get to a critical level, 0.6 volts, we see electrons start to be drawn into the base here on the left. But the majority of electrons are pulled across the depletion region into the collector, and current is able to flow. So imagine you're all, do you guys still call the 4 degrees Dooleys? Yes or no? Okay, that was like a dated, when I was a cadet, that wasn't a cool term to use. It was like too dated. Okay, so imagine the Dooleys are going to go take Spirit Hill, or at least one of the cadets says, we're going to go take Spirit Hill, and he gets everybody running, but he's really planning, he's on the Saigon side of the terrazzo. He's really planning to run down the stairs to where the tailor shop is. Is there still a tailor shop down there? Okay, but not all, like, hundreds of cadets can fit down the tailor shop stairway. So most of them missed the fact that the first guy turned into the stairwell, and they just keep running past the stairwell like lemmings jumping off a cliff. That's what's happening with the electrons. And how would we turn off the flow of electrons? I'm going to see if my analogies are working. So then how would we get the electrons to stop? Jason, can you answer that?
No, I can't.
Okay. If we close the door to the tailor shop, then that first cadet won't try to run in there, and nothing will happen. So on the transistor, how would we start off this flow of current?
You shut off the voltage at the base.
At the base, very good. Yeah, the base is our control valve. Okay, so if I turn down this base current, this base voltage, no current can flow from the base to the emitter. So no current will flow from collector to emitter. Okay, it doesn't matter what the voltage is between the collector and the emitter. If I don't have the base voltage set right, nothing will happen. Okay, that's our control knob, is the base. So see again what happens when I turn up the base. We get tons of current flow, and in reality, there's usually about 100 times more current flowing from the collector to the emitter. Why am I saying collector from emitter, even though the blue dots are going emitter to collector?
It's just how we define flow of electrons. We kind of defined it backwards. We mentioned that last class briefly.
Exactly. Benjamin Franklin didn't know what electrons were and didn't know that they were negatively charged. Okay, so he defined the direction of current flow, and electrons go in the opposite direction of current flow. So even though we see blue dots going this way, imagine the current as like a green line going from collector into the emitter, and from the base into the emitter. Okay? All right, let's hide this thing and we'll talk about this some more. Okay, so down here, so we talk about the collector current is really what we want. We're using the base current to control the collector current, but it's the collector current that we care about. The increase in current is known as the gain, and that's depicted as beta, or also on data sheets, we'll see it as this H sub Fe. So gain, beta, or H sub Fe. It's typically about 100, but it can be anywhere from 50 to 250. It depends on the BJT, and we can look that up on the data sheet, and we'll look at one a little bit later, probably next class. So can we fill in the blank here? It's a what amplifier?
Current.
Current, very good. Current amplifier. Are you guys okay with that? Would you like a current amplifier? Would you like a different type of amplifier? I don't even know what I'm asking. What about a voltage amplifier?
So I know for 460 we used like I don't know if it was an amp. We used like an op amp to increase our voltage output so that we could read our like get strain from that.
Right. You were so in that situation, it was convenient to be able to amplify voltage. Right. This does not amplify voltage; it amplifies current. But these are the basic building blocks that go into an op amp, and you can put these together in different combinations and get the ability to amplify voltage. In a few lessons, we're going to learn about FETs, field effect transistors, and they work with voltages. Okay, so for now, this is the simplest of these devices, and we're going to learn about these as a basis. But these are we'll use these to control motors, so that's why we're interested in them. They're very useful for that. Okay, let's move along. So we would like to know, being engineers, so what we just went over was kind of the physics, but being engineers, we want to be able to use these things. So how do we use them? How do we make them work for our purposes? So I mentioned this already a few different times, but we need to forward bias the transistor in order for it to work correctly. Let's add to our notes here. I want to draw an actual circuit diagram. We wouldn't draw this in a circuit. This would confuse people. It's not a transistor. What a transistor looks like in a diagram is what's shown down here on the lower right. You put an arrow here indicating the emitter, and this is the collector. So collector, emitter. You wouldn't, in a real like circuit diagram, you wouldn't write PCE, but we're learning, so we're going to do it. Wait. Up here, you have some, we're going to call the load. This is what, well, this is V naught. VC would be down here. On that BS, and so there's usually some power source here and connected to ground. So there's a couple things going on here. What the main thing we're going to use transistors for in this class especially is to turn things on and off. We're going to use it as a switch. So we have something we want to turn on and off. That's the load. So this might be a motor. It might be a light, something like that. It's usually something that requires more current than your microcontroller can produce. Because if all we wanted to do was turn on an LED with low current, we can do that right now with our Mega, no problem. But we can't run bigger motors with our Mega. We don't have enough current. So we're going to use this device to get more current. So we put something in here called the load that we're going to turn on and off using the transistor. So this thing right here in the center is the actual transistor, and we'll talk about different elements of this. This is the base resistor. So when using a transistor in a circuit, we add different components to it. Okay, we'll talk about those in a second. All right, so back to the slide. So we must be forward biased to do anything. So VBE has to be greater than 0.6 volts. VBE is the voltage drop from the base to the emitter. So this, from here to here, that's VBE. Really, I didn't draw that line correctly. Here to here. Okay, that's VBE. And then we're going to have VCE over here. So the slide is asking like a what? VBE greater than 0.6, like
a diode.
Like a diode, okay? And VCB, from voltage from C to B, has to be greater than 0.6 volts, and it's usually a lot more than that. And we have this condition, C has to be greater than B, has to be greater than E, like we have right here, okay? So this a transistor, a BJT, has three modes it can operate in. It can operate as an amplifier, where we're amplifying current, we're multiplying current by a constant, or can act as a switch, in which case we say it's in saturation mode. So over here, and it has this breakdown region, which we wouldn't operate it in. Okay, so when it's in this amplifier region, as we increase the base to emitter voltage, and we increase the current flow from the base into the emitter, the current flow from the collector to the emitter increases proportionally. And it's subject to this constitutive law right here. In general, we're not going to use transistors this way in our class. We're going to use it as a switch. as we increase this base voltage even higher, eventually we get to a point where it's called saturated, meaning it can't provide any more current, no matter how much we turn up the knob. You know, think about it like if you're listening to speakers, maybe your headphones, you turn up the volume, at some point you can keep pushing the volume up button and nothing happens, because you've reached the limit of what the circuit can provide as far as current. Okay? And so we'll learn how to map that out on these devices. But we want to use that, we're actually going to want to use these devices in this saturated region, and I'll show you why a little bit later. Okay, so how does this work? Take a look at this plot here and take note of what these units and labels are. So we have IC, and I have this plot over on our notes also. So this is IC on this axis, and go down, go over. This is VCE on this axis. So we're plotting the current through the device, IC, as a function of the collector to emitter voltage. Looking for a different color. Uh-oh. Okay, so we have IC, and we'll have IB here. Okay, scrolling down a little bit. So look at this slide over here. These family of curves are the base currents. So we've been talking about how a base current controls the collector current. So when I increase the current at the base, I'm moving up these black lines, okay? And we determine the operating point of the transistor based on what its collector to emitter voltage is set up to be, and then we can determine the collector current. So I'll show you how that works. Next slide. Okay, so the first sort of analysis problem we're going to do is how to predict transistor behavior. So we want to find the operating point of the transistor. So we start by, we need to know, red. We'll need VCE, and we'll need the base current. If we have VCE and we have the base current, we can figure out where we are on this plot, and we'll know the collector current. So the first step, step one, is to calculate the base current. How do we calculate current in this class?
Ohm's law.
Ooh, close. It's that three-letter acronym I like to foot stomp a lot.
KVL.
KVL, let's do KVL. Okay, and you're thinking now, what is he even talking about? If we look at this, here's the base. This forms a circuit from this source through this resistor through the transistor to ground. Okay, so we're going to do KVL for the base. We start with VS. Okay, then we go minus the voltage drop through that resistor. So what's that voltage drop going to be? You can look over here too.
It's IRB, so like IBRB.
Good, very good. IBRB. Okay, then we go to we get to the transistor. What do we do with that? Well, we're treating it like a diode, What would it be if it was a diode?
0.6.
Very good. So we just assume a voltage drop of 0.6 volts. And we set that equal to 0. Now, could we solve for the base current? Assuming we knew what the resistor was and we knew what the source voltage was. Can someone nod?
Yes, sir.
Yeah, can we solve for that? Okay, IB would then equal BS minus 0.6 volts over RB. And that's the base current. Okay, so now we have the base current. So that means we know which of these black lines we're on. Okay. Step 2 is the output load circuit. So we're going to graph the load line. On top of this figure over here. Okay, so how do we do that? Well, first of all, what is the load line? I haven't even really told you, but let's go through it and you'll see what I mean. What we're going to do is draw on here a line that indicates where the transistor is set up to operate in. Okay, so we can do that by looking at the other elements of the circuit. So the first part is we're going to use IC and VCE to do that. Get back to my pen. So need IC and VCE. Okay. So if we look at this plot again, look at the axis. So there's 0, the origin's right here is 0, 0. So we're going to do some logic here. So let's imagine that IC is 0. So if IC equals 0, that means no current is flowing. When IC is 0, the voltage drop across the transistor, so VCE, has to equal V naught, which is this voltage up here. Uh-oh. Are you guys still with me? I got a message on my screen that I was dropping out. Okay.
Yes, sir.
Okay, so again, let's remember Ohm's law. Maybe this may be a little confusing right now. If there's no current flowing through RC, what's the voltage drop on RC?
0.
0. Okay, do you agree with that, Jason? Okay, that's what Ohm's law tells us. So if there's no current drop, if there's no voltage drop over RC, we know from KVL that V0 has to drop to ground between here and there. So there's only two parts of this circuit. There's this voltage drop, VRC, and there's this voltage drop, VCE. So if the voltage drop across the resistor is 0, then the voltage drop from C to E must be all of V naught. Okay, and that's because no current is flowing. A resistor doesn't draw any voltage if there's no current flowing through it. Okay, so that gives us our first point on this line. So that's going to be something like a point right here. That's where the collector current is 0, and the VCE has to be whatever we've set it up in the circuit, V0. Okay, then we do the same kind of logic game, but on the other side of the plot. If VCE equals 0, that would mean that all the voltage is being dropped across the collector or across the resistor, the load. So we can do KVL, we can say V naught minus I C RC equals 0. So IC has to be V naught over RC. And we just calculate what that is, and we plot that up here. Then we draw a line. That's our load line. So down here on this slide here, these bullets are pointing to these different points. So point D is right there. And this point Q then is our operating point. In the previous step, we calculated the base current. So we would figure out what line we're on here. And then wherever that intersects, that's our operating point. And that tells us what the collector current is. And it tells us what the collector emitter voltage is. So remember, in plotting this load line, we made assumptions about, we looked at extreme cases when IC is 0 or when VCE is 0, but that's not what is actually going on in this circuit. That's just helping us get it set up. What's actually going on is whatever the operating point tells us is going on. So in this case, and I totally just made up stuff here in plotting this line, but in this case, it's telling us that the collector current is about 4 milliamps and the collector to emitter voltage drop is about 10 volts. Okay. Any questions on that? So you would use this process if I gave you a circuit where everything was on there and it said, tell me what the current is through the collector in this with this transistor. Okay. That's generally not what we do as engineers. What do we do as engineers?
Build the system.
Build the system where we design it, right? We would like to be able to design it to work in a certain way. Okay, we'll get to that in a minute. All right, so again, so look at this plot on the lower left here. We've seen how we make this line and how we figure out where that Q is. Now we can talk a little bit more about what is going to happen to the transistor for different situations. So I mentioned before, there's 3 operating regions. The easiest to understand is this cutoff region, the red, okay? This is where nothing is happening, okay? There's no base current. Remember, where is base current shown on this plot? Find your mute buttons.
Is that the
curved lines that go across? You have a few different ones.
Who's saying that? Is that Joe?
Yes, sir.
Perfect. Say that again louder. I kind of talked over you.
It's just the line. You have a couple of them going across the graph.
These black lines.
Yeah.
All right. Can you see my cursor? Yeah. These black lines is the base current. Okay. So the cutoff region would be that the base current is so low, it's not turned on. We haven't forward biased it. Nothing can happen. All right. So the collector current, the left axis, is low. It's 0. Okay. As we turn up the base current, we climb these black lines and we get into the green region. That's the active region. It's acting as an amplifier when it's in this region. So we can, in this region, we can plot the load line. We can figure out where it intersects with whatever the base current is, and we can figure out what the collector current is. Look at these numbers. It's not a coincidence that we have 20 lined up with 2 and 40 lined up with 4. And it would be the same in this plot over here on our notes. Okay. What is the gain of this transistor? What was gain again?
Is whatever the factor in which IB was raised by to I.
Yeah, it's that beta. Very good. So IC equals beta times IB. So beta is IC divided by IB. So could you look at this plot and tell me what the gain of that transistor is?
Would it be 100?
It is. It's 100 in this example. That might be a GR question. Any questions on that? Okay, so in this active region, the base current gets multiplied by 100, and that's the collector current. Okay. Now, what happens is as we continue to increase that base current, we get over here into this blue region. The blue region is the saturation region. And saturation region is actually where we want to operate most of the time. In the saturation region, the collector current is maximized. It's at its highest point, and VCE is very low. So why is that good? We want VCE to be low. Adam, you have your hand up. Do you have a question?
Yes, sir. Could you, going back to the gain, I'm just a little confused why it's 100. I guess when I look at it, I'm seeing 110 for IB and IC, which,
it's
where
the
do you
units.
get the numbers off the charts? Oh,
Good
okay.
question.
That makes
So
sense.
milliamps and microamps.
Got it.
Okay. So I'm telling you that in this saturation region, VCE is very low. And that's a good thing. Why is that good?
Is that going back to where we said VC needs to be greater than VB is greater than VE? And if that's really big, then VB is going to have to be really big to.
That's a good thought. That's not why. Okay. What is the purpose of this transistor in the way we're going to use it in our engineering designs? What are we going to use this for?
To increase current. Well, amplify current.
You can use it for that. We're going to use it to turn. Yeah, we're going to use it as a switch to turn things on and off. So say we're turning on a motor. Do I want the energy that I'm using going into the motor, going into the transistor, going into both, going into neither?
The motor?
Yeah, we want to turn a motor. So if I've got like a 6-volt battery, I want all that 6 volts going into the motor. I don't want it going into my switch. Imagine like your light switch in your dorm room. What if your dorm room light switch sucked up half the energy that your lights needed? That'd be a pretty terrible design, right? So if we can make VCE as low as possible, that means we're losing the least amount of energy in the transistor. And all the energy is going into the motor instead. That's what we want. So we're going to learn to design these to be in that saturation region. We will design our circuits so the BJT is saturated.